What we want to discuss today is a topic that's been mulled over to a great extent on YouTube and other places. We have these repeating nines, and people are telling you it's equal to one, and the answer to why is not readily available. But the short answer is infinite decimal expansions are limits. Limits. And that's always a tricky concept to discuss. So I won't really attempt to do that. Talk about what are limits, but limits do extend ideas, and so let me make my argument about why you might believe this. Let's start with the decimal expansion of rational numbers. Rational numbers are ratios of integers. If you have 1/4, that's going to be 0.25. And this expansion terminates, and we have 1/3, which most people do accept as repeating threes. And this does not terminate. And here's another one. This is 1/5. This also terminates, okay? Now, we don't have to have a 1 in the numerator. We could have something else. 5/9 is 0.5 repeating. Now the question is, how do we get these? How do we get these decimal expansions? And why are they so prevalent? Okay, and the answer to that is to be understood that the numbers that are being discussed are on the real line, which is your x-axis, and every point on the real line should have a decimal expansion according to tradition, okay? And if you just have ratios of integers, there are holes in the real line, and so you certainly need to start with these and know their decimal expansions. And we know if we're looking at things. For example, nobody has the tax rate being an infinite decimal. It's just not happening, okay? And which decimals terminate, like 1/5 and 1/4? Well, the decimals that terminate have only 2s and 5s in the denominator. Twos and 5s. When they're in lowest terms, they can only have 2s and 5s, and that's because base 10. That's because you're in base 10, okay? And 2 and 5 are special denominators in base 10, and combinations of those are special. So now 9 is also special. It's one less than the base. If you're looking for the decimal expansion in any base, the 9s in the base 10 and the 3s in base 4 and the 1s in base 2, which is binary. But the point is that those are special because those give you overlaps. Okay, they give you numbers that have two decimal expansions. So let's see how a rational number gets its decimal expansion. What is used to get that? And the answer is long division. Long division. So let's look at an example. Here's 1/7, okay? We want its decimal expansion. What are we going to do? We're going to divide the numerator into the denominator. So this 1/7 is in lowest terms, it's not 2/14 or, something else. It's 1/7 in lowest terms. So you put the numerator in over here, it becomes the dividend. And we want to, now, all these decimal expansions of rational numbers, ratios of integers, are periodic. I won't define it. We'll see it. We'll see it here. So we have, this is 1 times 7 is 7. And we're going to bring down, this is 4 7s are 28. And then this is 2 7s are 14. And 8 7s are 56. And 5 7s are 35. And 7 7s are 49. But before I go on, let's look at the remainders. The key is how many possible remainders on division by 7. How many possible remainders are there? The remainders are 0, 1, 2, 3, 4, 5, and 6. Okay, those are the remainders. If you don't have the non-zero remainders, there are just 6 of them. You have a denominator of 7, and it's the lowest term is 6. The denominator is 29 in lowest terms, then there's 28 possible non-zero remainders. The denominator is 29, it'd be 28 possible remainders. Here we have, this is kind of a first remainder. This is the second remainder. This is the third remainder. This is the fourth remainder. This is the fifth remainder. This is the sixth remainder. So you have 1, 2, 3, 4, 5, 6. So this remainder here, we're going to be done now. We're going to have to repeat. Or 0. Well, it's going to have to repeat because we're going to run out of we ran out of remainders. So this is a 1, but the 1 already came up. It already came up over here. Yeah. So it's 142857, 142857, 142857, boom, 142857. So this is what periodic means. The period is 6. So without defining it, I'm explaining what periodic means. Now, you're supposed to question me and tell me I cannot use long division to get the 9s. Okay, but the 9s are special in that the 9s, we're going to divide 1 into 1 and get the 9s. Okay? The reason the nines are special is that that one digit doesn't mess up things like a two-digit number. 10 doesn't have one digit in base 10. So 10 has two digits. So we'll try. We don't. We say 0 here, and we put a 9 here because not 9 is 1 times 9 is 9. We subtract, we get 1. We bring down to 0. This is a 9. 1 times 9 is 9. Okay, and so there it is. I obtained the nines from dividing 1 into 1 because you don't get a two-digit remainder when you have the 9 there. And so that's my plausibility argument for now. One thing that's true is that the nines intrude on everything else. If you have 4.9 repeating, it's a half. And that's the overlap. The nines create overlaps with every terminating decimal expansion. Okay, and there's the example. If you terminate, you can go one digit less and put a bunch of nines out there, and it works. So that's the end of that story, and I hope you liked it.